So in this one, we're pulling two crates, but we're pulling them sort of at an angle like this. They're identical crates. Each one is 50 kilograms, and each one has the same amount of friction with the ground. Okay, so the coefficient is 0.25 on that. All right. Now, so what we're going to do here is we're going to take this thing apart and treat it like it's two different pieces. All right. So let's take a look at piece A first. All right. So we've got our weight here, WA, and a normal force, N sub A. Okay. And then some friction back this way. We'll call it FA. And then it feels some tension here. Okay. And so let's go ahead and do our free body diagram while we're thinking about the forces on that guy. Okay, so here we are. And then we've got our weight down. Okay, so that's mg. The two crates are identical, so really I don't need to put A on there. And then we got the normal force in A. And our friction, FA. And our tension, T. Okay, just like that. Okay, so we've got some relationships that pop out of that right away, which is that the normal force A is mg. Okay, and then the second relationship we get out of there is that FA is the tension. Okay, now FA is actually mu times NA, and so then we make one more substitution and we got mu times mg. Okay, and so there's our first relationship that we got out of this thing. Okay, so let's just hang on to that for a second. Hopefully it'll come back to help us out. Okay, now let's get our forces on the other one. Okay, so we got WB, and again that's really just mg. I don't need to put a B on there, but you know. Okay, and then we're going to have a normal force. Okay, here in B. We've got some tension backwards. Okay, it's the same tension we saw just a second ago. And then we've got our friction right here like this. Okay, all right, so let's make a free body diagram on this one. Okay. It's a little more complicated, but still not bad. All right, tension's there. Here's P and NB and mg. Our weight. Okay, 1, 2, 3, 4. There we go. Okay, now if we look at what's happening, okay, so in the x direction, some of those forces, then I've got minus t plus p sub x is 0, okay? Or t is equal to p sub x, but p sub x is p cosine 30 degrees, okay? So that's where our horizontal forces got us. Let's see where the vertical forces get us, okay? Here we go. Okay, so we've got NB plus PY minus mg. Okay, all right. Oh, I forgot my friction. How'd you guys let me forget the friction on that? Oops. How did you let me forget that? There we go. And it's in here too, minus F. Just like that, okay? And so that's going to come in here like this, okay? And that's actually FB. There we go, just like that. Okay, I think I got it. I think I got it taken care of there. Okay, so in B, Py mg is equal to 0. Okay, and so we're going to have NB plus P sine theta is mg. Okay, just like that. Okay, now if we solve that for NB here, NB is going to be mg minus P sine 30. Sine 30 degrees. There we go. Okay. Now, the reason for doing that is because now with our friction at B, we're going to write here mu times NB, and then we got the plus T is P cosine 30 degrees. Okay. And then if we plug in this information here for NB, okay, then it turns out we're going to have mu onto mg minus P sine theta. Well, I don't know why I keep doing that. It's 30 degrees plus T, and we found T is mu mg, okay, is equal to P cosine 30 degrees. Okay, just like that. All right, there we go. Okay, so now we've got one equation with a single unknown P. Okay, and that will be the limit because we did things like setting F equal over here to the friction. Then that means we're operating at a maximum. Okay, we're already, so we've set this whole thing up with our equations like it is operating maximally. Okay, and so P there, once we get a number for P, it will be the maximum value for P. Okay, all right, there we go. So that's number 3.